Hi everyone. So I am going to go through a transport phenomena question for transport phenomena 1 on Navier-Stokes. So first thing I'm going to do is I am going to share the problem here, and feel free to go back to this screen. I am going to share a different screen of me doing the actual problem, but feel free to go pause the video, go back to the beginning of this to look at the question or take a picture of this question, whatever you need to do to have it side by side. So first thing first is to read the question. So in a journal bearing a long, solid cylindrical shaft with a radius of R1 is being rotated inside a stationary cylindrical tube with an inner radius of R2, and R2 is greater than R1. The velocity of the shaft surface is V1 is equal to R1 omega, where omega is the angular velocity constant. The annular space between the shaft and the tube is filled with a lubricant that is a Newtonian fluid of constant density, and the rotation of the shaft produces laminar flow in the fluid. Assume that the flow is steady and the air pressure at both ends of the annular space is at atmospheric. Part A, carefully draw and label a diagram of the system and include a sketch of your best guess at the shape of the lubricant velocity profile. Part B is simplify the equation of continuity in the Navier-Stokes equations for the system to obtain a differential equation describing the variation of velocity within the lubricant. Part C is state the boundary conditions needed to solve the velocity as a function of position within the lubricant. And part D is solve your differential equations for the lubricant velocity profile. So first things first is to start off with drawing a picture or a diagram. So I'm going to move over to my notepad. So first I'm going to go ahead, and I know it showed a picture on the actual question, but I am going to draw my own. And I'm going to start with one from the side profile just because I understand it a little bit better that way. Didn't mean to pick yellow, actually. I'm going to start off. So this is, what I'm drawing here first is the stationary cylindrical tube in which the long cylindrical solid shaft is being rotated within. These lines on the end just means that it is stationary, just so I remember for myself. And inside here is going to be the shaft that is the solid shaft that is not moving. I just am going to color that in a little bit so I remember that it's solid. So no flow is happening. So no flow is happening within that at all. So we don't really have to worry about the inside of that. Then I'm going to kind of cut this through the middle. I'm sorry that this isn't the straightest line in the world. And I'm going to label, because it says R1 is going to be from this spot here to the end of this shaft. So that's R1. Sorry if it's a little hard to read. And from there to here, this is R2. And so from then on, we are going to create or decide on a coordinates-like system. So personally, this is cylindrical in my opinion. So I am going to, or you would choose cylindrical because you're working with cylindrical objects. So this is going to be the z-axis here, and this is going to be the r-axis here. You are going to need that for the rest of the problem, but just so you know. And then something else is that it mentions that the pressure at both ends of the space is atmospheric. So the pressure here is PATM, and the pressure, and that's for both here and here. It's all the same. And then same with these. So next is something else that they gave us. Just want to write it down so I know where it is that the velocity one is equal to R1. So now that we have that, we now have to draw the velocity profile. So that's what this first question is asking for. It says carefully draw and label a diagram of the system, which is what I just did, and include a sketch of your best guess of the shape of the lubricant velocity profile. So the lubricant is all in here in this area that I just colored in green. That's all the lubricant. So I'm going to take that off really quick. So what it's asking for is what the actual fluid looks like, the actual velocity profile of this fluid. So there's a few rules when it comes to this kind of problem regarding like, what's the name of them? So regarding the actual flow, you have a few like boundary conditions. So that's something that you have like a solid fluid boundary condition, a liquid boundary condition, and a liquid gas boundary condition. In this case, it is a little bit easier to see from like a different view. So from right here, I'm just going to draw a new picture as well. I'm going to draw it over here of what this looks like from like top angle. So we have, again, this is like the outside, that's stationary. And then this is the solid shaft in the inside. And we know that this is moving this way, which I'm actually going to write on here too. And that's theta. And this is moving this way, which is angular velocity or theta, whichever one. But I'm going to write this angular velocity over here. So now that we have that, there's these things called the no-slip conditions, which are like our boundary conditions as mentioned before. So with that being said, the velocity of this item is going to be the same that it is on here. It's called the no-slip. So right here on this, I'm actually going to do a different color at this green point. This line, this tube is not moving. It's actually completely stationary. So that means that the flow at this point is also going to be completely stationary. So this is just going to be a straight line here. I'm going to do this in yellow. It's going to be a straight line here. So the velocity isn't really moving at this point. So then as this solid shaft in the middle is moving in this direction, as I mentioned before. So this point is also going to be moving in this direction. So then you're going to end up with a velocity profile that looks like this. And I'm just going to draw the arrows with red. So it's going to be moving in this direction. So that's what your velocity profile looks like. Now, if I wanted to draw it on the actual like sideways diagram, it's going to look something like this. Draw it in green. And it is going to look something like this. But it is a lot easier to see on this diagram here. So now that we have part A done, where we had to draw the diagram and draw the velocity profile, we can move on to part B. So this is part A. Part A. And I'm just gonna highlight that really quick. Now we have part B. Like that really quick. All right. So part B says simplify the equation of continuity and the Navier-Stokes equations for the system to obtain a differential equation describing the variation of velocity within the lubricant. So the continuity equation is, so for the equations of continuity, there's a few different ones. I'm gonna move my screen down a little bit. There's the Cartesian coordinates, cylindrical coordinates, and spherical coordinates. Right now we're working with cylindrical coordinates, which are I'm just gonna abbreviate that. And this is R, theta, and Z, which I showed above right here. So we're using cylindrical coordinates. So the equation of continuity is, I'm just gonna take a second to write this down real quick. That is not a 2, this is oops. What are we looking at the wrong equation? Sorry about that. So sorry about that. Okay. So we have plus 1 over R, W R, R, 3R plus 1 over R theta, theta. Let's see. Oops. That's all equal to 0. Oh, okay. So with that, first thing I like to do is make a few assumptions first. So this is just something you can do like on the side of your paper that helps with the problem in the end. So one of the first assumptions is that it is laminar flow. This problem is including laminar flow. Unless it says it's turbulent flow, you assume laminar. The second assumption that I typically make is that it says that it's steady flow, which means that it is not changing with time. So the d over dt is going to be 0. The third is that it is an incompressible. Because it's a liquid. So that means that rho is constant. The fourth assumption that I make is where it gets a little bit tricky. So this is where we kind of have to use the picture. So we have 3 velocities that we could have. So we have v in the z direction, v in the r direction, and v in the theta direction. Typically in these problems, like one of them is not equal to 0, but the other 2 are. So that's when we use this here r and z coordinate system. So just going to start off with, so let's start off with v of c. So if we have a, so the z direction is this direction here. So if I have a particle here and I have a particle here, do they have different velocities? They do not. So that would mean that vz is equal to 0. Same thing with, erase those particles really quick. And then same thing, so the r direction, which is this direction, So if I have a particle here and I have a particle here, are their velocities going to be different? No. So go back down and I say, okay, well, VR is equal to 0, which means that V theta is most likely not going to be equal to 0. And you can attest by that because you are changing the velocity as you go around in this direction here. You can also use this diagram to do the same thing. So that gives us our fourth assumption. And last but not least, which also this means that function 4, last but not least, we assume that it is fully developed. Unless it says otherwise, then you usually assume that it's fully developed. But in that case, that means that u of v theta over d theta is not a 2, partial derivative, I promise. That is equal to 0. So now with these assumptions, we can determine what to do with the cylindrical coordinate. So I'm just going to move down a little bit. So with that being said, so I have this and I'm going to say, all right, so as we change the pressure with time, it is not changing because nothing's changing with time according to our number 2 value here, or our number 2 assumption here. So that would mean this is 0. Oh, I'm actually going to do this. This is 0. Our VR, we determined that VR is 0 here. So this whole equation here is going to be 0. On this one, we determined that V of 0 over V of 0 is equal to 0 as well, which is our fifth assumption. So this is all going to be going to 0. And our VZ is also 0. So we are also going to be setting that equal to 0. So then we end up with 0 is equal to 0, which is what we want in a problem like this. Typically means it's a little bit easier to solve. So now that we have part A and then the first part of part B of the cylindrical coordinate down, we are going to move on to the second part of the part B where it says the Navier-Stokes equations to determine Navier-Stokes equations for this. And all right, so these equations are a little bit longer. They look a little bit scarier, but they are not as bad as they look. I'm just going to continue down here so I have a little bit more room. But again, we're going to be using the cylindrical coordinates, and the equation that we want for this is going to be the one with theta involved, because we determined that theta is not equal to 0. So we have, all right, so bear with me while I write this equation down. This is a kind of long equation, so I'm just gonna write the rest of it down here. I'm sorry that my rows and my P's look very similar, but this up here is a row. Trying to put a tail on it of some sort, and this is a P. I'm running out of room here. Sorry about the way this looks. That's all in the bracket as well. And the last part of that. Okay, so sorry about how that's written, but it is a very, very long equation. So now we just have to go through this and determine which parts of it are equal to 0 and see what we're kind of left with. The first thing is I'm going to start on the left side. And we mentioned in our assumptions that it's steady flow, so it does not change with time. So this is going to be equal to 0. VR is again equal to 0, so this is going to be equal to 0. V theta, dv theta over dv theta is equal to 0 because it's fully developed. And then vz is equal to 0. So this is 0. Then here VR is equal to 0, so all that multiplied together is equal to 0. So on the one side, we have 0. One side of the equal sign, we have 0. And then moving back, so here we have the pressure is not changing. So I'm going to go back to here. So you see right here, we have PATM on both sides. So the pressure is the same on both sides. So that's when this would be 0. And then we have this here where it is V theta over dr, which we are actually going to keep this. This is going to be the first one we keep so far. It is not going to be equal to 0. And then we have, again, V theta over d theta. It's going to be 0 because it's fully developed. V theta is not a function of dz, so this is going to be 0 as well. And here, VR is equal to 0, so that's 0. And last but not least, this is the gravity function here. And in our case, we're in a horizontal, so there's no gravity horizontally. So it's going to be equal to 0. So then we are just left with 0 is equal to mu times v over dr of 1 over r v over r of r v theta. And that is it. So with that being said, we are moving on and solving for v theta. So here we can just divide both sides by mu to get rid of it. And we end up with 0 is equal to d over dr, 1 over r, d over dr, r v theta. And then we will be taking the integral of both sides. So we'll do that. And when you take the integral of both sides, you end up with a constant on this side. And then here, it actually just ends up being equal to the inside here. So you end up with 1 over r, v over dr of r v theta. So again, well, first you're going to multiply both sides by r just to get rid of this pesky r on the front here. And you're going to end up with C1r is equal to d over dr of r v theta. So then same thing, we're going to want to take the integral of that again just to get rid of this d of dr. And take the integral of that. When you take the integral again, you end up with C1r squared over 2 plus, and then you have to add another constant. So that is equal to, and that's just going to be equal to the inside here again, which is r v theta. I'm going to divide both sides by r to get that b theta alone. So then you end up with b theta is equal to C1r over 2 plus C2 over r. And that is the part B completely gone through. Moving on to part C, which is to state the boundary conditions needed to solve for velocity as a function of position with the lubricant. So some of the boundary conditions I kind of mentioned before, but I am going to write them out really quickly. So sorry about my messy handwriting. So the first one is a solid to a fluid. When the fluid velocity is equal to the velocity at solid surface. It's also known as the no slip, like I mentioned before. Next is a liquid-liquid interface, which where velocity components are continuous. Just gonna write that through the interface. It's another way to write the no slip condition. And then last but not least is the liquid gas interface, where the momentum or shear stress is assumed to be 0. All right, so with that being said, going back to our pictures before when we drew our velocity profile, we did use the boundary conditions that we're gonna kind of figure out ourselves now. So first, I'm gonna go back down really quick, and we're gonna say we have the first boundary condition. So I'm gonna label it boundary condition 1, and it is going to be, sorry for going back and forth, but we are going to do it at this here where I just put that star in red. So at that point, we know that this solid surface is not moving. So it is completely stationary. So right here, the velocity is 0. That is also going to be like right here if you look on this diagram. So like right here. So we have when the radius is equal to R2, because that's where that point is, the velocity of theta is going to be equal to 0 because of the no slip condition. And the second boundary condition that we're going to have is going to be when R is equal to R1. And I'll go back up to that picture. R1 is going to be, I'm going to draw a yellow star at this point here. And we know that that solid, the solid cylindrical shaft in the middle is moving. So, and we know the velocity at that point. That is right here. This was given to us. So, at when the radius is equal to R1, we know that the velocity of theta is equal to that equation that they gave us is R1. Perfect. And these are both due to no slip conditions. boundary conditions. Okay, so that is part C. C is all done. I'm just going to draw a nice box around it. Sorry, it's not perfect. All right, so then we are going to move on to part D. I'm going to highlight those really quick. All right, so easy to find later. All right, so then last but not least, part D says to solve your differential equations for the lubricant velocity profile. Obviously, this is going to be like the most math part of this problem. So I'm just going to rewrite our, oh, not what I wanted. I'm going to rewrite our velocity equation that we figured out earlier. Oh, that's not, oh, I believe that's what it was. Yep, so right here. Oh, perfect. And using the first boundary condition, BC1, I'm just going to use that boundary condition where R is equal to R2 and B theta is equal to 0. So in this case, I'm just going to plug it into this master equation up here, velocity of theta. And then I'm going to say B theta is 0. I'm just going to put it in parentheses so you know where I'm plugging them in at. And C1 is, or this is C1 R2 over 2 plus C2 over R2. So when we have that equation, we have a 0 on one side, so we are just going to solve for C1 in this case. You can solve for C1 or C2. In my case, I'm just going to solve for C1 because it's a little bit easier for me. So first I'm going to subtract C2 over R2 on both sides. And we're going to get C2, negative C2 over R2 is equal to C1 R2 over 2. And then I'm just going to multiply both sides by 2. Then you get negative 2C2 over R2 is equal to the C1 R2. And last but not least, I'm just going to divide both sides by R2. And C1 ends up equaling negative 2C2 over R2 squared. So I'm just going to put a little yellow star next to that because I know we're going to need it later. And I'm going to move on to using boundary condition number 2, which we have when R is equal to R1, we have V theta is equal to R1. Perfect. So I'm going to do the same thing. I'm going to plug that into this equation with the red star next to it and go from there. So V theta is R1, that's equal to C1 R1 2 plus C2 R1. So perfect. And in this case, I'm going to solve for C2 just because we already solved for C1 and we know that what that's equal to. So actually, before I do that, I'm actually going to plug in this C2 or C1 right over here into this equation, so then I can really solve for C2. So we're going to end up with R1 is equal to, this is where C1 comes in, so negative 2C2 over R2 squared times R1 over 2 plus C2 over R1. So there aren't any C1s left in this equation, so we are able to solve for C2. So this 2 ends up canceling out with this one. And then you're left with R1 is equal to negative C2 R1 over R2 squared plus C2 over R1. And then just doing a little bit more algebra, I'm gonna factor out the C2 R1, and we're gonna get R1 is equal to C2 R1 1 over R1 squared. I also took the negative C out, multiplied by -1. And you end up with this. So then solving for C2, you end up getting C2 is equal to over 1 over R1 squared minus 1 over R2 squared. So now we have both of these equations, C1 and C2, we know what they're equal to. So then we are going to go back to this equation here. Sorry, that looks like that. I'm going to redraw that. Go back to that equation, which I'm actually going to write again down here, which was phi of theta is equal to C1R over 2 plus C2 over R. So then we're going to plug in that C1 right here and the C2 here. So now we have phi theta R equal to have negative 2 C2 over R2 squared multiplied by oh, I'm sorry. You know what? Totally. I'll substitute that in. Okay. R over 2 plus then C2, which is over 1 over R1 squared minus 1 over R2 squared. That's all over R. Notice how we still have a C2 here. So again, we got to plug that in here. Then we get phi of theta equal to 2 over R2 squared multiplied by this again. Multiplied by R. I'm actually gonna write that R over here, make it easier. Plus, same thing over here. And again, I'm gonna write this a little bit easier to read. Multiply this by 1 over R, which is the same thing as dividing by R. So when you simplify all of that, factor out some of the same components that are in both, you end up with, factor this out of both sides, divided by 1 over R minus R over R2 squared. And that is the final answer. So just to go through it again really quick, just really quickly, first thing we did was we drew our diagrams and had our best sketch of the velocity profile. Then we simplified the equation of continuity and the Navier-Stokes equation, which I'm actually going to label up here really quick. I did that here. Oh, perfect. Did that, got a velocity of theta. Then C, we stated our boundary conditions needed to solve for the velocity as a function of the position, which happened here. And then last but not least, we solved the differential equations for the lubricant velocity profile and ended up with our final answer here. All right, well, thank you so much, and I hope this made things a lot easier.